Saturday Morning Physics is dedicated to the purpose of engaging our audiences of all ages to learn about cutting-edge science, science policy, and the impact of science and technology on our daily lives. Let's remember that science is an essential human desire, the need to understand the universe from the smallest to the largest and everything in between, and that science transcends all borders, cultures, and peoples. And with that, I want to remind you that Saturday Morning Physics is made possible by you, by your generous contributions. And also, we are grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, and the Van Loo Family Endowment, and for today's event, the Pulikeshi Dayalu, Astrophysics Fund. So I'm really pleased to welcome Praveen Dayalu, who's a professor of neurology in our medical school, to say a few words.
Thank you so much, Tim. It's really nice to be here. My parents moved to Ann Arbor in 2013 from Seattle to be with family and grandkids, and I remember my dad was really, really nervous about the winters here. I mean, he knew what gray was, but not what bitter cold was. And it's safe to say that really Saturday Morning Physics was one of those things that sustained him through the winter. I mean, he would come here on the bus, and he didn't mind being here in the cold. And he would boast to other people, friends and family who lived in other places, just how amazing it was that we had this thing where the lay public could file into a room like this and hear about cutting-edge science for free every week. And it was really, he loved it. It meant a lot to him. So it was entirely logical after he passed that myself and then my mom, Nimi, my sisters, Rashmi and Archana would get together and do something and support one of these lectures in perpetuity. So we're grateful, really grateful for the opportunity to do this, and grateful for everybody who's here and who continues to attend these. As for this speaker and this topic, my father was always so happy about not only the veterans like Fred Adams, who spoke here regularly, but also about new young voices who were presenting their own work. And he would always make a point of saying, oh, this person is speaking, they're a junior person in their career, it'll be really interesting to see how they present and what they do. And he knew the value of opportunities like this for young scientists. And so we're very grateful to Juliette Becker. The topic, well, I will say that my father knew when there was a strange idea that seemed a little hard to accept, but then again, that's probably most of theoretical physics. He came here not to be told what is, but maybe to be persuaded what might be, right? And I think that's part of what makes these sessions so interesting. As I was trying to think about what would he actually have been saying in the run-up to this, anticipating this session, because he'd be talking about it. And I think he would be like, yeah, I can't believe it. How do you have life on a planet if the star is dead? I don't know. We'll see what Juliette Becker has to say. I don't know. But it'll be really interesting. And all the more, even if you had such a planet, can you imagine a couple of alien life forms standing there next to the ocean, holding tentacles, and they look up, and instead of a sunset, you have a piddly white dwarf. who wants to see that? So I'm sure he would have said something like that, and then we would have said something like, "No, Dad, you got it all wrong. It is a star of small stature that is melanin challenged. Get it right." So anyway, we are super excited to hear what you have to present. Thank you so much, everybody.
In about 1 minute. Okay. Well, anyway, thank you so much for your family's generous support of Saturday Morning Physics and for the memory of your father and his devotion to Saturday Morning Physics and curiosity and skepticism. For more information for everyone about supporting Saturday Morning Physics, please go to saturdaymorningphysics.org. Now, moving on, at the end of Juliette's lecture today, we will have a question and answer session. So those online and also those in the room, if you like, you will be able to ask questions. We'll have the microphones out. But also you can email your questions to physics@umich.edu. So it's my great pleasure to introduce today's speaker, Professor Juliette Becker from the University of Wisconsin Department of Astronomy. We're so fortunate to have you stay a little longer to present and add Saturday Morning Physics to your very busy schedule and visit to Ann Arbor. Juliette gave the astronomy colloquium on Thursday on the formation of hot Jupiter-like planets. Juliette grew up in Washington State. She had a passion for astronomy, not surprising, and running. And then she did her undergraduate work at Caltech, and then came here to the University of Michigan Astronomy Department to pursue her PhD studies under Fred Adams, whom Praveen mentioned, and who's here in the audience. And he's also, by the way, the director of the Line Weber Center, whose public lecture I mentioned earlier. And Fred also actually gave the first Dayalu family supported lecture a couple of years ago. So Juliette's received her PhD here in 2019. She did her dissertation on exoplanets, and that dissertation was highly recognized with the ProQuest Distinguished Dissertation Award and the U of M Baldwin Prize. Juliette then moved, I guess, back to Caltech, and this is interesting, the 51 Pegasi B Fellow. So, speaking of white dwarfs, but, so we can ask her exactly what that means. And then to the University of Wisconsin-Madison in 2023. Professor Becker has broad interests, in particular in the life cycles, dynamics, and habitability of planets and the potential for life planets. So today she'll tell us about how a planet survives a star's transition to a white dwarf. Thanks, and thanks for joining us, Juliette.
Thank you all so much for the warm welcome. It is really such an honor to be back talking to the Saturday Morning Physics crowd. I remember when I was a graduate student coming here and being so impressed that there was such a large community of people so passionate about physics in Ann Arbor. And now I'm back talking to you all. It's extremely exciting. So today I'm going to be telling you about something that is really a speculative research topic that we've been working for the past few years to try and understand if it really would work or not. And that is the possibility of life on planets orbiting white dwarfs, which are dead low-mass stars like the sun. Now, before I get started, I want to be very clear. Astronomers have not yet found life anywhere outside of Earth, and let alone finding it on these particular type of planets. But we have been searching, and each new telescope gives us new ways to search. So part of the motivation of thinking about places in the galaxy where life could be that looks so different to where we see it here on Earth is trying to guide future missions that will determine the best places to look for life. With that, a lot of the reason I've been thinking so much about habitability and life is I'm a part of the Wisconsin Center for Origins Research, which is a new interdisciplinary center at the University of Wisconsin-Madison that tries to use interdisciplinary tactics to study questions relating to how life arises. So I've really benefited from talking to colleagues in chemistry and atmospheric science and biology about what they think about how life develops. But today I'm going to be thinking about life from a pretty astronomical, kind of astronomy typical perspective, which is when I'm thinking about life, I am thinking mainly about planets that could host the conditions that appear to be conducive to the development of life. Now, our search for life is still kind of in basic stages. So what we usually assume when we think about what creates habitable conditions is we assume that for a planet to potentially have the conditions needed to develop life, you probably have to have water. And this water needs to be in a liquid form. And the reasons for this are that water is the universal solvent. So it allows for both chemical reactions that could allow life to develop, but also it allows for molecules and atoms to interact with each other. So water provides a medium to allow for the interaction between the building blocks of life. So, the chemists have long thoughts about this, but as an astronomer, they have convinced me that if we want to find habitable conditions in the galaxy, we need to find a place where water is in liquid form. So this is something that astronomers have been using as our criteria for searching for candidates that might have life for a long time. And we do this by defining something called the habitable zone. So here is a NASA artist's rendition of kind of what the habitable zone means. So here, this is the TRAPPIST-1 system model, but the 7 planets in the system span a very different range of climate locations. So for the ones that are closest to the star, the surface temperature of the planet is hot enough that if you did just dump a cup of water on its surface, it would immediately just boil off. So these planets are too hot to support habitable conditions if you assume that habitable conditions require liquid water. In contrast, in the outer part of the system, far away from the star, where you get a lot less power from stellar radiation. So your incoming heat from stellar photons is going to be a lot lower. These planets could potentially be too cold to host liquid water. So they would look more like the icy moons in the outer solar system, where any water would be frozen solid in an ice shell covering the planet. In between these two regions is something we call the habitable zone. And the habitable zone just means that you could have surface water in a liquid form on the planet. So some people also call this the Goldilocks zone because it is neither too hot or too cold. It's just exactly the right temperature for surface water. In the solar system, this habitable zone has indeed allowed for habitable conditions on our own planet. But again, thinking about habitability and life in terms of only just our own planet and how life developed on it is probably a little bit limited if we want to understand the diversity of life that could exist in the galaxy and the universe. So the next slide that I'm going to show you is a plot of the planets that were known in 1988. So this plot has 2 axes. On the x-axis, we have the orbital period. So this is how long it takes the planet to orbit around its star once, so a year. So Earth, you'll see marked here by a little clip art Earth and an E, has an orbital period of 365.25 days, because that's how long it takes us to go around the sun. Then on the y-axis here, we have the mass of the planet. So larger, heavier planets like Jupiter, Saturn, the gas giants are higher on this plot. And then smaller planets like the terrestrial planets are lower on this plot. Now, maybe luckily for me, I don't have enough time to talk through every single planet that has been discovered since 1988. So what I'm going to show you next is just an animation where one point is going to plop up on the chart for each planet that was discovered via a variety of methods. And these planets range from a couple planets that were discovered in 1992 around a neutron star, and then in 1995, 51 Pegasi b, a hot Jupiter, for which the fellowship I had in my postdoc was named. And then again, 6,000 other planets will pop up that I do not know the names of all of them. So I'll start that animation. And what you're going to notice is it starts kind of slow. So early on, the technology had really just gotten to the point that we started to barely be able to make these discoveries. And most of these early discoveries that are popping up are of larger planets, kind of similar in mass to Jupiter. And these were often discovered with like ground-based telescopes operated by universities. When we get to 2009, we had the launch of the first space transit hunting mission, Kepler. And the big point of, there it went. So all of those points that just popped up were discovered by a space telescope that was designed just to hunt for planets. In 2018, there was another space telescope, which I'll talk a little bit about later, TESS. And as we get to the end of this animation in 2026, what you'll notice is that this exoplanet population, so all of these planets that just popped up on the screen orbit other stars in our galaxy. All of these planets have very diverse properties. So, what does this mean for our understanding of life? It means that if we really want to understand life outside of the solar system, we need to understand a huge diversity of environments that doesn't necessarily look exactly like the solar system. So our goal then is to expand the search for habitable planets, and instead of looking for only Earth twin planets that are exactly like Earth, orbiting stars exactly like the sun, we want to expand and look around stars that are also very different from the sun. For an example of this, I'm going to put up this diagram I put up earlier of the solar system. So again, in too close to the star, you're going to be too hot for water to be in liquid form. Too far away from the star, you'll be too cold for water to be in liquid form, and there's this Goldilocks zone that we call the habitable zone, where water can be liquid. I'm now going to put up a second system that was discovered by a team searching for planets around really small stars. And what you might not notice, but I want you to pay attention to, is that this system up here has been enlarged 25 times compared to its actual size. So this entire system would fit inside this tiny circle on the bottom. So these planets are around a star that is less than 10% the mass of the sun. And there are many reasons why stars that are this small are very different from the sun in terms of how they would support habitable conditions. So we think these small stars might form more planets. We think they might be more magnetically active. There's a laundry list of things that are very different about these types of stars compared to the sun. But one thing that we learned from this population of planets that I showed you previously was that this is an environment that we should be looking for habitable conditions. Because indeed, in this system, in the TRAPPIST-1 system, we actually have a higher number of potentially habitable planets than we do in our own solar system. So, with that said, hopefully I've motivated you that so far, astronomy has done a pretty good job of starting to look in places that are not exactly like the Earth for habitable conditions. So next, I'm going to ask you to consider something a little bit more different than just a star of a different mass. So I'm going to ask you to think about stars that have actually lived an entire life and run out of hydrogen to fuse and started to evolve into stellar remnants. So to do that, I'm going to show you first an animation. So once the sun eventually does run out of hydrogen to fuse, which will probably happen in another 5 billion years, what will happen is it will start to evolve into something we call a red giant. So I'm going to show an animation of what that might look like. So during the red giant phase, the sun will expand, first to about 10 times its current radius, and then as it runs out of the last little bits of fuel that it can burn, it'll expand up to about 100 times its current radius. Now what this means is it means that the planets will be engulfed. And actually, scientists have done some pretty complete studies of what will happen to all the terrestrial planets in this case, and it appears that even, unfortunately, Earth will also be engulfed during this phase. Now, this is not great for habitability on Earth. We got a timer of about 5 billion years, so we got to maybe think about doing something about that. But this is not the end of the system. So when the star goes red giant, it doesn't destroy the entire system. It just changes it into a new form. So after this phase happens and the star becomes a red giant, the star loses about half of its mass in an outflowing stellar wind. So this is something that we can actually see happening. And this is a real image taken by the Hubble Space Telescope of this process, which we call a planetary nebula. So material is being thrown off from something that used to be a star, kind of like the sun. And what's left right there at the center in this image is going to be the remnant core of the star, a white dwarf. So a white dwarf is basically what's left behind after the sun has gone through this process of expanding into a red giant, becoming a planetary nebula, and throwing off half of its mass. What's left behind will just be a tiny, condensed piece of material supported by electron degeneracy pressure rather than the fusion that supports the sun. And the fact that this object is supported by electron degeneracy pressure instead of fusion means that it looks a lot different from a normal sun-like star. It'll actually be physically about the same size as the Earth. Now, this is an object, again, about half the mass of the sun, but physically the same size as the Earth. This is a pretty extreme environment, so this is something we'll be back to briefly. But first, I've now told you the story of what will happen to the sun once it runs out of fuel to burn. But the next question is, why do I think that white dwarfs are good targets for characterizing habitable planets? So the first piece of evidence is observational. It is extremely difficult to, even if which we have, found planets that we think can be targets for biosignature searches. Those searches are really hard to do. So people have tried to use space telescopes, such as the James Webb Space Telescope, to do this type of characterization on, for example, the TRAPPIST planets that I showed you previously. But it's just an extremely noisy observation, and it's really hard to characterize the planet's atmosphere and actually see what's in it. White dwarfs, on the other hand, this is now a simulated James Webb spectrum from 2020, made by some scientists who said, okay, well, what if we found a terrestrial planet that had biosignatures around a white dwarf? How would we be able to find them if they did exist? And what they found is that unlike planets around normal sun-like stars, which you have a lot of noise, white dwarfs are actually pretty quiet, a nice background, but also, since the planet is so large compared to the white dwarf itself, you actually have a really favorable contrast ratio, and you can see the atmosphere of the planet a lot better. So, potentially, again, if we found a white dwarf that had a planet that was a good target for biosignature searches, it would mean that JWST would have an easier time finding the biosignature than it currently does. Now, next question is, do we actually think that planets can exist near the white dwarf? Because what I just showed you in the previous animation was that Mercury, Venus, Earth will all be destroyed. So the entire inner part of a planetary system is going to be cleared out and destroyed during the process of stellar evolution that turns a star like the sun into a white dwarf. So I'm going to start by motivating this question with a couple decades of evidence for not planets, but that planets orbiting white dwarfs, but that planets have been transported close to white dwarfs. And I'm going to start to do that by asking you to think about the idea of gravitational acceleration. So I have here the equation for gravitational acceleration. This is something where, depending on the object you're standing on, you will be accelerated towards the object with a different speed. So on Earth, you probably all know g is going to accelerate us downwards about 9.8 meters per second squared. If you were standing on the surface of the sun, then it would be about 25 times larger, about 270 meters per second squared. Now, there's something very unique about white dwarfs due to their combination of a really large mass and a really small radius. So if we take our expression for the surface gravity and we plug in the fact that the mass is only about half the mass of a sun-like star, so this symbol right here denotes the mass of the sun, but then their radii are about the same radius as Earth. So it's shrunk significantly compared to what its radius was on the main sequence. This allows us to compute what the surface gravity should be on a white dwarf. And you can kind of imagine, like on Earth, you accelerate a certain amount down. On Sun, it's more. And on a white dwarf, it's going to be extremely more. So 100,000 to 1,000,000 meters per second squared. This is extremely fast. What it means is it means if anything is on the surface of the white dwarf, it is going to immediately settle down below the level that we, the observers, can see. So if you were to take a rock and you were to throw it onto a white dwarf, it would not sit on the surface and be observable. It would sink down into the white dwarf because of this extremely high surface gravity. And scientists did some calculations and found that actually the timescale for this happening is often almost instantaneous in cosmological timescales. So what does this mean? Back in the 1990s, people started looking at white dwarfs. And what I'm showing now is an example of what you might expect to see when you look like a white dwarf. So this is a spectrum. So on the x-axis here, I have the wavelength of light that is being observed. And then on the y-axis here, I have the amount of light that you're seeing at that particular wavelength of light. So you can think of the x-axis as being slightly different colors, and then the y-axis is how much light you're seeing at that color. So chemists, and also astronomers, like to use these types of spectra to figure out what chemically is in the object that they're looking at. So this spectrum that I'm showing you now is kind of the typical spectrum that you'd expect to see for a white dwarf, where you're only really going to see hydrogen lines, because anything heavier than that, any metals, anything more complex, would just shrink down below the surface and then not be visible. So based on the fact that white dwarfs have really high surface gravities, this is what you'd expect to see. But this is not what people often saw. So instead, now this is the actual spectrum for this particular source. There's this feature corresponding to calcium, which is not expected to be something that you would actually see in a white dwarf. So what this meant, and this again was work that was done in the 1990s, people continued to observe these white dwarfs until the present day and found that a huge percentage, 35 to 50% of them, had metal lines, which meant there were metals on the surface of the white dwarf. Now, this is surprising because I just told you those metal lines shouldn't be visible. The metals should have sunk down already. So what this means is it means that there is active material polluting the white dwarf basically as we are looking at it. And what people started to realize in the 2010s is that what this means is the fact that we see so many polluted white dwarfs with metal lines is that about a third of systems are actually actively accreting material. And when people looked at what that material was chemically, they found that it corresponded possibly to planets. So some of the spectra had chemicals that you might find in the mantle of a planet like the Earth. Some of them had molecules and abundances that you would expect to find in the core of a planet like the Earth. So there was this evidence for a very long time, for decades, that planetary material was somehow being transported to the white dwarf surface and then being deposited on top of it. So for a long time, we had this evidence that planetary material was being transported into the white dwarf, but we didn't actually know of any intact surviving planets orbiting white dwarfs close to their surfaces. Enter the TESS spacecraft. So TESS, the Transiting Exoplanet Survey Satellite, was launched in 2018, and its goal was to survey the entire sky looking for transits. So you might be asking or wondering, what is a transit? To do that, we are going to do a quick demonstration here. So what we have here is a big bulb representing a typical star. And we'll say this soccer ball is going to be a planet. So a typical star and a typical planet, the planet will be a lot smaller than the star. But wait, white dwarfs are about the same size as the planet. So we'll swap out our star with a smaller bulb. So now we have our star, our planet, which is about the same physical size. This is the white dwarf. This is a planet. What we're going to do now is we're going to pretend that right here is the TESS spacecraft. So what TESS does is it just stares at the sky for long periods of time, watching stars, just looking at the light that's coming from them. So what you see up in the middle panel of the screen here is going to be the amount of light in lux that we are receiving on this detector from this bulb. So I'm just going to turn this on, and we're going to collect some data. And look at this data. Looks pretty flat. Maybe some small variations, partially probably due to measurement error. This is exactly what you'd expect to see if you were the TESS spacecraft staring at a star that's just sitting there and doing nothing. All right, so next, let's imagine that this star is not alone. This star has a planet orbiting around it. If that is the case, then what you're going to see is you're going to see the planet. If you're lucky, if you get lucky about the geometry of the planet's orbit, then you'll see the planet pass in between the star and the telescope, so TESS, our detector, and it'll look kind of like this. And then the orbit, you might have the planet has to go all the way around the star, and then eventually it'll get back and do the same thing again. All right, I lost my second transit. We can take a look at the first one here. So barring here where something happened, what happened when I moved the ball in front of the background star is there was a dip in the amount of light that was detected by our detector here. This is what TESS does. TESS just stares at the sky, looks at all the stars, and waits for dips that look exactly like this. Now, I'm going to leave this image up, and I'm going to give you on the next slide what TESS actually saw when it looked at a white dwarf. So go ahead and take a look at the shape of this light curve. And we have time here is on the x-axis, brightness is on the y-axis. And what do you notice? How many people think that looks kind of similar? Okay, good. I agree with you. Right, so this is exactly what, when we were looking at a white dwarf with TESS, this is exactly what we saw. We saw a dip in the light that we were receiving from the white dwarf. And this dip in light, at first, we were kind of surprised because it appeared that about half of the light that we were receiving from the white dwarf was being blocked out. Now, normally, when you use this method to discover planets, planets are much, much smaller than their host stars. So you might only block out like 1% or so of the light. But for this particular white dwarf, about half of its light was being blocked out. So we got this data from the TESS spacecraft and needed to verify what was happening. Because it's possible that this signal that we just saw could be due to a planet orbiting a star, but it could also be due to something else, like a false positive. So what we did is we got a bunch of additional data using telescopes on the ground. And actually, some of these telescopes were provided by amateur astronomers. So this one right up here in blue, this was taken by an amateur astronomer. And the reason that this was such an amazing event to observe from the ground was because, again, half of the light from the white dwarf was being blocked out when this object passed in front of it. So it turned out, after combining all of these different transit light curves together, we were able to figure out that this particular white dwarf had an intact giant planet orbiting around it. So a planet that we think is kind of like Jupiter, but completely intact, not destroyed, not accreting onto the star, just kind of a normal planet living a normal life. So, question is, how did it get there? Because as I said earlier, the phases of stellar evolution that takes a star through the red giant phase probably should have destroyed something sitting there. So we thought about it a lot and tried to figure out an explanation and came up with the following idea. So right now, what we see is we see a Jupiter mass planet orbiting around a white dwarf. But we know that when the sun or the star was on the main sequence, it went through this red giant phase and expanded. So the planet was not there originally. So we think what happened instead is the planet instead started out on a much more distant, further out orbit when the star was living a normal life like the sun. And then afterwards, it had to migrate into its observed orbit. So something happened after the white dwarf formed that took this planet from a far out orbit inwards. Now, what could that be? One option is there could be additional planets in the system that interacted with this planet and sent it flying inwards. And then another explanation is this white dwarf actually has some nearby stellar companions. And so this planet could have also interacted with those stellar companions, and they could have gravitationally affected its orbit and caused it to move inwards after the white dwarf formed. The third option is a stellar flyby. So maybe it was not a planet in the system or a star in the system, but it was actually another star flying by the system that perturbed the planet. So this was the first ever discovery of an intact giant planet, or I guess I should say an intact planet of any type, transiting a white dwarf. It is not the only example we have of close-in planets. So I'm going to give you a couple other examples. So one of them was discovered in 2019, but it was an accreting planet. So we think that this planet is being actively destroyed and accreting material onto the white dwarf, which is exactly the process that creates the pollution that we see in so much of the white dwarf population. And then finally, there is also evidence from a different space telescope that around a different white dwarf, there is a dust cloud orbiting. And it appears to be a dust cloud that has some larger pieces and some smaller pieces. And this is maybe evidence that there used to be a planetesimal or a planet that has been ripped apart by tidal forces. This particular one, this is still a transit light curve, the same one that we just all made together. The difference is that this one doesn't have beautiful transit events like we made because it's not a single object orbiting, it's a cloud of debris and dust and rocks. Okay, so hopefully at this point you are convinced that planetary material is transported inwards to white dwarfs quite often, and we actually have at least, well, we have one piece of evidence of an intact giant planet. But the next question is, can these planets, which are transported inwards, actually be habitable? Because the one that we found in 2020 using the test data, that one was a gas giant, a Jupiter-like planet. We don't really think that's a good condition for life to develop. Even if it was at the right temperature, it'd be kind of hard. So the next plot I'm going to show you is going to show you what we think the habitable location around a white dwarf is. So on the x-axis, this is the distance away from the white dwarf. AU is an astronomical unit. The distance between the sun and the earth is 1 AU. So the distances that I'm looking at on this chart are 1 to 4% of that value. This is very, very physically close to the white dwarf. Then on the y-axis, I have the white dwarf age. Now, the colored region here, this is the range of distances where, at any time, you could have habitable conditions. You could have liquid water. And the reason that this is changing as time goes on is because white dwarfs are not powered by nuclear fusion the way that sun-like stars are. Instead, they are slowly cooling and contracting and radiating away that energy. But the result is that they get cooler and cooler with time and dimmer with time. So this means that the place where planets could be habitable will also change with time. Here is where roughly the planet that we discovered with the test data in 2020 would lie. So this planet is a little bit too cold at the current white dwarf's age to be habitable. If it had existed in the same location at earlier times, then maybe it could have been the right temperature, but it probably wouldn't have been a good temperature for a very long time, and additionally, it's a Jupiter, so not the best place for life to develop. So takeaway from this plot, if you're going to take away one thing, is just that the habitable zone location for a white dwarf is extremely close to its surface. It's very close in. Even compared to the plots that I showed you previously of the TRAPPIST-1 planets, this habitable zone is going to be even closer to the white dwarf's surface. Okay, so next question is, we know where the habitable zone is. It's close to the white dwarf's surface. We know that there are planets and planetary material that get to that location, but how do planets reach that location? How can you take a planet that was used to live far out in the system and it survived the red giant phase, or how do you create a planet and put it in a habitable orbit? What I'm going to show now is an infographic that shows kind of the two theories that we've come up with. So in this infographic, we're going to start with, on the main sequence, planets will exist in some configuration. We think there's a lot of diversity between different planetary systems. So some of them have a lot of planets, like TRAPPIST-1 or the solar system. Some of them only have a couple planets or even one. Some of them will have a lot of Earth-like planets that are just slightly larger than Earth. Some of them might have different planets with very different masses. But in any case, you start with some planetary system that has multiple planets, and some of them are maybe in the habitable zone. The next stage is that once the host star reaches the end of its life, it becomes a red giant. And this means that it will expand in size and it'll engulf the habitable zone, the previous habitable zone on the main sequence. So at this point, any planets that hosted life while the star was on the main sequence in the habitable zone are probably going to be disrupted or lost. However, not everything is disrupted or lost. Outer planets in the system that are far enough away that they're not either physically engulfed by the red giant or tidally destroyed will probably be okay. Third stage, you go through this planetary nebula phase where the star will shed its outer layers. What's left behind becomes a white dwarf, but also during this time, the orbits of the planets will kind of reshuffle because the star losing mass means the orbits have to expand to approximately conserve angular momentum. So this is what happens pre-white dwarf formation. Now I have two different hypotheses for how planets may reach the habitable zone. So we're going to start by looking at the one over here in blue, first generation planet formation. So first generation planet formation is called that because the planet is a first generation planet. It was one that was born when the star itself was forming, very early. So at the very beginning when the sun formed, all of our known planets formed, they would be first generation planets. So if you have such planets, if you have some type of dynamical instability, so for example, you could have multiple planets in the system that interact with each other, and if the interactions are sufficiently strong, one of them can be sent into a high eccentricity orbit. So this diagram here shows a high eccentricity orbit means you come pretty close to the white dwarf at some times, and then you spend a lot of time pretty far away. It's an orbit very similar to a comet's orbit. Next up, tidal forces can circularize the planetary orbit. And these tidal forces will also do other things that we'll talk about in a few minutes. But long term, what these will do to an orbit is they will take something that starts out looking like a comet's orbit, and it will turn it into something that looks more like the Earth's orbit, very circular. Now, this last stage is a little bit of a jump, because these first two stages will put the planet in some location that you can kind of predict. But some small fraction of these planets that migrate in this way might end up in the habitable zone. Now, white dwarf 1856b, the one I just showed you, the intact giant planet discovered with TESS, that one did not quite end up in the habitable zone. But maybe there are other planets that migrated slightly differently that did end up in the habitable zone. So this is option one, first generation planet formation. The second option is over here in orange, second generation planet formation. So what second generation means is that these planets did not exist when the star was a sun-like star fusing hydrogen into helium. These did not exist at that time. Instead, these planets formed after the star went through the processes of stellar evolution and became a white dwarf. So the hypothesis here is you have the same first step of dynamical instability, but instead of exciting the eccentricity of a potentially habitable planet, you excite the eccentricity of a giant planet, like white dwarf 1856b, or maybe even something larger, like a stellar companion or a brown dwarf. Now, if this planet, again, it's going to be on this orbit where it comes really close to the white dwarf and then it goes far away and close and far. If it comes just a little bit too close to the white dwarf, then tidal forces will rip it apart. And what you'll be left with in that case is a debris disk of material, kind of like what we saw in that white dwarf system that had just the transit curve that looked like a mess. It was just dust and debris transiting. But you'll be left with just a debris disk. So it is possible that planets could form from that disk of material in the same way that they form from protoplanetary disks early in the sun's history. This second-generation planet formation theory actually has been invoked in the past to explain planets around pulsars. So I mentioned way back at the beginning of this that the first 2 planets discovered were actually orbiting a pulsar, a neutron star, and theories have demonstrated since those were discovered over the past 3 decades that those planets had to form via a second-generation pathway. So we already know that second-generation planet formation does operate around neutron stars. We have not found any evidence that it has to operate around white dwarfs, but it is potentially plausible that it does. All right, so we have these 2 pathways that you could take a planet or create a planet and put it in the habitable zone. But there is one more challenge, which is, can these planets actually have water? These processes that I've just described are very different from the processes that Earth went through in attaining its water. So it's kind of a question of, given how extreme their histories are, could these planets even retain surface water? So there are 2 main challenges to retaining water. The first of these is light. So on Earth, our surface, we get almost all of our energy from just solar radiation. Now, if you're Mercury or if you're in too close to the star, the amount of radiation that you get is too much, makes your temperature too high, and any water you have on your surface will boil off. So light is a challenge to retaining water. If you have too much light, you have too much radiation from your host star, then you won't be able to retain water. But there's actually another challenge to retaining water, and it is one that I've now mentioned a few times in the past few slides as being relevant to both first and second generation planets around white dwarfs, which is tidal forces. So with that, we have yet another demonstration that Monica is going to help me with. So what is a tidal force? Tidal forces are essentially just when you have a gravitational force on an object that's not the same across the entire object. So you have forces that are different in one place than another. What this looks like for planets is it looks like the planet is essentially getting squished. So what Monica is doing now is measuring the temperature of this ball that represents a planet. And what are we at? 71 degrees. All right, 71.6 degrees. Everybody remember that. Now we're going to, Monica is simulating what would happen to a planet if it were being squished by gravitational forces. So this is something that anytime you have tidal forces, this squishing happens. On Earth, this squishing is not too bad from the moon, so it just kind of very gently squishes the oceans. There are other objects where the squishing can do a lot more. So Io, Jupiter's inner Galilean satellite, is squished so extremely by perturbations from Jupiter that it is highly volcanic and has no surface water. So now our ball has been squished. Let's measure the temperature again. All right, take a look at that. If anyone remembers, Thank you, Monica. That was some very successful tidal forces. All right, so you all see how many people did remember the value that we got the first time and see, is this value hotter than it was before? Hotter. All right, excellent. Yeah, it's a couple degrees hotter. Now, this was only the squishing and forces that we humans could provide on a planet. But what happens to planets during these processes is a lot more violent. So it's going to be a lot worse than just 2 degrees of increase in temperature for a planet. So the second challenge to retaining water is going to be this tidal forces. Because these tidal forces, if they increase the temperature of your planet too much, you can have a lot of problems. You can have your water becomes too hot and it'll boil off. So what this means is it means that a planet orbiting a white dwarf is subject to both of these 2 effects. So you have not only solar radiation providing heat from above, but you also have tidal forces squishing your planet and providing heat from below. So all of a sudden, keeping your water means not just having the appropriate amount of irradiation from your white dwarf, but it also means that you must be appropriately tidally squished so that you don't become too hot. Now, put back up the diagram I made, you will notice that both of these two processes had this tidal force happening. And there's even more ways that tidal forces can be a problem. So this is actually a pretty large challenge. If you want to have water on these planets around white dwarfs, which we think is important and imperative for life to develop, then you need to not be so hot that you lose all your surface water. So next up, let's look at exactly what happens to these planets as the star evolves and then also as these tidal forces occur. What I'm going to show you is some plots showing how different properties of a system might evolve. Now, up here, we have the luminosity of a star. So this part early on, this is just the normal main sequence end of a star's life. Then it starts to brighten. Here, right here is the red giant phase. And then you have thermal pulses as the star runs out of material to fuse. Right here, at this peak, is the point where you transition between being a red giant into the planetary nebula phase, and you're left with just a white dwarf behind. This fall off right here, where the brightness or the luminosity of the star is getting cooler and cooler and cooler, this is when the white dwarf is just cooling. So we have early main sequence, like normal life of a star, red giant phase, and then this whole part here is the white dwarf's evolution. So next, let's put up two more plots that are going to tell us what the mass of the star is doing, and then also what the orbits of planets might be doing. So the second panel here is the mass of the star. It's pretty constant, but then in that phase, that planetary nebula phase, about half of the mass is lost all at once. When that happens, the planetary orbits are going to expand. So I have here some planets that start out at kind of 3, 5 AU, and then are staying at pretty constant orbital radii, but then during this planetary nebula phases, their orbits expand a bit. Okay, next panel, we're going to see what is the temperature of the planet's surface during this entire evolution. Because not only are the planet's locations changing, which should make them colder, but then the star right here is also getting brighter, which will give the planets more energy from irradiation and make them hotter. So here's how the temperature evolves. You'll notice that, it's pretty stable for the star when it's just a normal sun-like star, but then it goes through this phase of getting really hot and then really cold. So now, the final piece of this calculation that I did was to check what happens to surface water. So let's say that you had an initial ocean on these planets and it was initially just a frozen ice shell. What would happen as this evolution occurred? And what you'll notice is that so these three lines correspond to different initial positions of the planets. So this bottom line is something at 4 AU, so interior to Jupiter's orbit by a little bit. Then we have something at 7 AU, 7 times as far away from the sun as the Earth is, and then finally something at 10. And what you'll notice from this plot is that the closer in planets, even if they survive this evolution, like the planets themselves physically survive, something at 4 AU will just lose its surface water during this process. And so even if it was transported in onto a habitable orbit, we might still have problems trying to develop life on this planet. Now, what about the tides? Because to take these planets that are at extremely large orbits and make them habitable, we have to go through this process of tidal evolution that has tidal forces. And this animation shows kind of what that evolution might look like, where you start with a high eccentricity. So you start with an orbit that looks more like a comet, and then you end with an orbit that looks circular. During this entire process, heat is being generated inside this planet. And what that means is it means that this tidal heat can take the water that was previously in a liquid form on your surface and evaporate it into the atmosphere. And once that water is evaporated into the atmosphere, it becomes even easier to remove than it was on the previous slide. So here's two more plots. I'm going to describe the panels before describing exactly what they mean. So the top panel here is the semi-major axis of the planet during this migration process where it's moving inwards. So it starts at a large separation from the star, and then it moves inwards as it tidally migrates. The next panel is the orbital eccentricity, which again starts out high and then gets lower and lower and lower. Now, this third panel, we'll look at this one, is an important one because it tells us how much heating is being generated by different sources. So the red line here is the amount of heat that's being input into the planet via tidal forces. And then the blue line is the amount of heat that's being inputted via radiation. So purple is the total amount of heat that's being generated by both of these two sources. And the important thing to note here is that, like, at early times, the heat generated by tides, by the squishing of the planet as it evolves and it comes so close to the white dwarf, this heat is actually a lot larger in quantity than the heat that the planet is getting from irradiation. So this does potentially mean at those times you're going to evaporate your planet's ocean into the atmosphere, and it'll be water vapor. To lose the ocean, as you'll notice here on this plot, we are not losing, or we're losing the entire ocean. We're not keeping any of it. And on this plot over here, we are keeping it. There is one thing that must be true to keep an ocean, and that is that you have to delay migration until later in the white dwarf's lifetime when it is not as bright and it doesn't have as much high energy irradiation. So the high energy irradiation can take the water vapor that's in the atmosphere, that tidal heating is evaporated into the atmosphere, and it can take that water vapor, it can break it apart into hydrogen and oxygen, and then it can take the hydrogen and just get rid of it entirely. So what you might be left with in this case here is an atmosphere that has apparently a lot of oxygen in it, but there's nothing left to recondense into water. However, if you can delay migration until later where there's not as much high energy radiation from the white dwarf, then you will not drive a net loss of oceans from the planet's surface. So this is just two plots, but if you make plots for a huge number of parameter combinations, then on this plot you can see how much water is remaining after this entire migration process. The entire process of like the star evolving, the planet orbit expanding, the planet being perturbed into a high eccentricity orbit, and then eventually the planet migrating inwards. So the x-axis is how far away the planet is from the star at the end of the simulation. And then on the y-axis, we have both the temperature of the white dwarf at the time the planet starts migrating, and then that also corresponds to an age of the white dwarf. So this is useful because it tells us which planets should retain water, but what we really want to know is we really want to know how this overlaps with the habitable zone. So here is the location of the habitable zone. So what this means is it means that this entire part of the plot where water survives, it'll probably be too cold. It'll be frozen. And this part right here probably will have boiled off. But there is this little bit of parameter space here where oceans survive and the planet ends in the habitable zone. So this is the place where surface water does survive the journey to the habitable zone. So for first-generation planets, for ones that existed when the star was born and lived its first life as a sun-like star, and then also survived the red giant phase, we can learn a couple things about how you might keep oceans. So the first thing that you got to do is the planet has got to survive. It can't be engulfed by the red giant or tidally destroyed. So this means it has to probably live pretty far out in the system. So for our own solar system, a gas giant or a moon of one of the gas giants they would survive. They'd be good. Next, you need to have one of a few things be true. You either need to have a huge amount of initial oceans so that everything that happens during this process that I just told you about, there's enough water that even if you lose most of it, you still have some left. The other option is you have to also be far enough away from the star that you retain some fraction of this ocean while the star evolves onto the red giant phase. And then finally, you also need to migrate in late. So you cannot reach your final orbit immediately after the white dwarf is formed. This has to happen later in its lifetime. if you do all of these things, then you can potentially keep water on a planet that formed early around a main sequence star and then migrated late to become a first-generation white dwarf habitable planet. All right, so that's option 1, hypothesis 1. Now, what about hypothesis 2? So in hypothesis 2, in second-generation planet formation, the planets form from a disk of material after the white dwarf is formed, and this allows us to miss a lot of the dangerous phases that I just described that first-generation planets face. However, it also creates a new potential problem, which is the fact that theories of second-generation planet formation suggest that you will form multiple planets via this process. So you won't have just a single planet, you'll have kind of a system of planets where you have multiple planets near each other. Now what this means is it means that these planets are going to interact gravitationally with each other. And this could cause a problem because as we learned from our tidal heating demo, if planets interact strongly with each other in a way that creates large tidal forces, which we think would happen if you have a habitable planet around a white dwarf with extra nearby planets, then this is going to increase the temperature of the planet from the bottom. So it's going to give some amount of heating to the interior of the planet, on top of the heat it's already getting from the white dwarf itself via photons, light, irradiation. Now, how is this a problem? This is a problem because even if you did have water on one of these planets, then it would be subject to the greenhouse effect. So the greenhouse effect, we have some good examples of in our own solar system. Basically what happens is you have photons irradiate a planet. The planet absorbs the energy from those as heat, and then it re-emits at a shorter frequency, longer wavelength. And this new quality of light is not able to escape from the atmosphere in the same way. So this is the same way a greenhouse works, where visible light from the sun gets in, but infrared re-radiated light can't get out, and so you basically just heat up the greenhouse. Same thing happens to a planet. And water vapor is actually a very successful greenhouse gas. In our own solar system, we have an example of this type of greenhouse heating and what it might do to a planet. So the example is Venus. So if we did not know anything about Venus's atmosphere, then we would expect it to be kind of a decent temperature, between like -40 to 50 degrees Celsius. However, Venus has an atmosphere that's like 96% CO2, which is an extremely effective greenhouse gas. And so what happens to Venus because of this is it essentially traps the heat. It's in this runaway greenhouse state where it is heated up significantly because the molecules in its atmosphere will not allow heat to escape. And so as a result, it is actually over 400 degrees Celsius. So this greenhouse heating can be a big problem. And scientists more than a decade ago pointed out that for planets around white dwarfs, even if they had surface water, and even if they were in the habitable zone, this effect could prevent them from being habitable and make them look more like Venus than like Earth, because they would have this runaway greenhouse effect where they would evaporate their surface oceans into the atmosphere, and then water vapor, being a very effective greenhouse gas, would then cause more heat to be trapped. And essentially, once the planet gets just to the right temperature, it just reaches a temperature where all of the oceans are evaporated into the atmosphere, then you will just never have liquid water again. You'll be stuck. So the question, this is kind of an issue that people have been worried about since 2013 for white dwarf planets. So the question is there a way to save a planet around a white dwarf from this effect? Could you prevent this runaway greenhouse from occurring? And the answer turns out to be yes, because of something that Einstein taught us in 1915, general relativity. So the effect of general relativity is to cause orbits to precess like a top. So this image here, made by the University of Oregon, is showing kind of the effect that GR has on a planet's orbit. It will kind of wander and precess through space instead of always pointing in the same direction. Now it turns out that this can significantly affect how planets interact with each other. And a student at the University of Wisconsin actually used work that Professor Fred Adams published in 2006 and pointed out that this GR could affect planetary orbits. But she used this to check if you added GR into the equations, since white dwarfs are massive and they're going to bend space-time and cause general relativistic precession for their planets the same way, but even stronger than the sun does for Mercury. So she checked to see how important GR was compared to the planet-planet forces that are causing this tidal squishing. And what she found is that there's actually a part of the habitable zone, not the whole thing, but part of it, where GR is actually a more important force than the force caused by the planets interacting, which causes the tidal squishing and the potential heating. If you are in a regime where this general relativistic precession is more important, this could actually stop a planet from being tidally squished by the other planet, because its motion would be dominated by the star instead of the other planet. So to test this, Eva did a large parameter sweep where she checked to see for different combinations of planets, when would a planet undergo a runaway greenhouse and when would it not. So she took a planet that was a kind of fiducial Earth-like planet orbiting in exactly the middle of the habitable zone with an atmosphere that is initially not dominated by water vapor. And then she first checked to see, could she reproduce the old result? Does the runaway greenhouse onset for different parameters of outer companion planet? So this is now where you're putting the second planet in the system. The first one is right in the middle of the habitable zone. And she found that only like a very small, and this is consistent with people have been saying for a decade, only a very small part of parameter space do you actually avoid the runaway greenhouse. Most of the time, if there's any additional planet in the system, which is something you'd expect to happen from second-generation planet formation, then there should be a runaway greenhouse and the planet should not be habitable. So next, what she did is she did the exact same thing, but added GR in. And when she did that, she found there was there's a much larger region where a planet could actually maintain habitable conditions and avoid the runaway greenhouse. And the only thing different between these two sweeps is adding GR into the equations. So what Eva's work showed is it showed that you really have to include every piece of the physics when trying to assess habitability of planets around white dwarfs, because even forces that normally we don't think are that important for habitability, like general relativity, which is usually ignored in habitability studies, can turn out to be really important since this is such an extreme environment. Okay, so hopefully I have now convinced you in the past roughly hour that we have found evidence that water could theoretically survive on planets around white dwarfs. I say theoretically because, again, we have no observational evidence of this happening yet. All we have is we have equations and computer simulations that tell us that there are ways that water could survive and could exist on a planet in the habitable zone of a white dwarf. So, what next? I'm going to put back up the animation that I showed you at the beginning, and this time I want you to pay attention to how there was very slow progress at first. Points jumped up pretty slowly for the first maybe decade and a half. And really, planet discoveries started to accelerate once technology got to the point where we could easily use methods like the transit method to discover planets in bulk. Previous studies have not really been optimized to find planets around white dwarfs. They are hard to find planets around because they are so small and because it takes actually a very short time for a planet to complete this transit across of the white dwarf because of how small it is. So as a result, right now, we are starting to make progress at discovering planets around white dwarfs using satellites like TESS, and we're also starting to do a good job at characterizing these planets using space telescopes like the James Webb Space Telescope. So there's currently a huge amount of ongoing work with the James Webb Space Telescope to both characterize the white dwarfs and the planets that we know about, but also to discover more planets around white dwarfs. And of course, the goal, the dream, would be to find a candidate that is in the habitable zone and then search to see if there is any evidence of biosignatures. With that, this is something that it will probably take us a few more years to actually make more progress on. There's actually currently a large effort ongoing, led by someone here at the University of Michigan, to search white dwarfs that have a lot of pollution and try to understand more about what's going on. So hopefully in the next few years, maybe decade, we'll have significant advances. And kind of like how slowly those planet discoveries populated, hopefully soon we'll get to the phase where we start to find white dwarf planets at that quicker phase. With that, thank you so much for letting me tell you about planets around white dwarfs, and I'd be very happy to take any questions that anyone has at this time.
Well, thank you so much, Juliette, for that wonderful talk. And also for engaging the Saturday morning physics tradition of using demos, and Monica as well, who stepped out for just a moment. So we have time for questions, and Juliette has graciously agreed to take your questions. So we'll start with questions in the room, but also a reminder for those of you who online would like to send a question, but do it soon, to physics@umich.edu. So we'll give like 30 more seconds for the room to settle down. Okay, first question.
I'm assuming the answer to the question is yes, but do planetary atmospheres survive the formation of the planetary nebula?
Yes, that's actually a very good question. It depends on where the planet is. Generally, the planets that we're looking at, the ones that can survive this phase, probably would keep their atmospheres. There are some planets that would have their atmospheres somewhat changed, but these ones would probably be okay.
Okay, thanks.
Okay, I'm going to interject actually two online questions that are related, and there's more than one asking the second. But the first one is, why liquid water?
Yeah, so it's a good question. The benefit that liquid water has for the development of the life, it acts as a solvent that allows things to interact with each other. So a lot of the theories that we have for the development of life on Earth required a pool of water or a body of water to allow the building blocks of life to interact. Otherwise, even if you're building the building blocks of life on your planet, if they can't interact with each other, then you won't develop life. So you need water to be liquid for that to happen. Ice is useful because if you did have something that could melt the ice later on, then maybe it could be in liquid form. But habitability studies generally focus on liquid water just because you probably need to have liquid water for a pretty long time to allow for enough time for life to develop.
Even the most primitive
Even the
forms of
most
life.
primitive, yes.
Okay, and then the follow-on to that, which came from multiple questioners, and maybe people in the room, is are there alternatives to water? And specifically methane was mentioned.
Yes, yeah, so methane is an interesting one because we have evidence in our own solar system that it can have similar weather cycles and pool like water can. Astronomers are focusing mainly on water because it is the most promising. I would not rule out the possibility for other solvents, I think, but I do think water is the probably most obvious solution. But it is a good idea. We should probably be thinking about life that doesn't necessarily develop the same way as it did on Earth.
Potentially a broader range of temperatures as well.
Yep, exactly.
Okay, here's a question.
My question is the time that a planet around a white dwarf would have for life to evolve. Around our star, we had like, 3 billion years. We got another 5 billion years to go or whatever. And you showed it a little bit, but it seems like it's continually changing. So what is that time length that life would have to evolve?
Yes, that is true. So it really would be very planet dependent. The time that people use to count a planet as being kind of in the continuously habitable zone, so having conditions that are good enough for life for long enough that we think life could develop, is about 3 billion years. So the planets on There we go. The planets on this plot that would be good candidates are ones that exist in the habitable zone for 3 million years, so this region. Ones that have shorter lifetimes than that are probably not good candidates for developing life.
You.
First, I'd like to say thank you very much for that. Was a very, very cool talk. You had me really on the edge of my seat. So, I was thinking in the habitable zone, the planet would have to be roughly, I think the plot said 100 times closer to its planet than the Earth is to our sun. And in our solar system, Mercury is quite close, but not 100 times closer. And he's really whipping around the sun fast. So there's centripetal forces, I would imagine, at play. Given that hypothetically, that planet would have to be so close to the white dwarf, he'd have to be, I think, whipping around very quick. The orbital period would be very, very small. Does that have any impact on the formation of water?
Yeah, so that's a great question. So something I didn't have the chance to mention today is that due to how close these planets are to their star, there's a very high chance they would be tidally locked. So they would have one face that always faces the white dwarf and another face that is dark and does not. This makes models of what the surfaces actually look like slightly more complicated. So within like the last maybe 1 year, people have started to do climate models of what would the climate look like on this planet. But you could very well have a planet where there are habitable conditions on part of the planet, but the rest of the planet would not be habitable.
One of our listeners wanted a little more information about the stellar evolution and specifically why the transition to red giant and then white dwarf. You know, what drives that?
Yes. So basically when the sun is on the main sequence, it's producing energy and radiation via fusing hydrogen to helium in its core. And then this process, the two hydrogen atoms have a little bit more mass than the number of hydrogen atoms has a little more mass than the helium atoms that are produced. And so the result is radiated away as photons. But this only works until you're out of hydrogen. And then you no longer have that force to sustain you. And so at that point, you start to go through the red giant branch where you start, basically the star tries fusing everything that it has left to fuse. And then eventually runs out completely of material to fuse. So it's basically the sun running out of fuel drives this end of its lifetime and the beginning of the stellar evolution. And then the planetary nebula phase occurs because the star basically cannot hold on to all of its mass compared to the pressure pushing it outwards. And so gravity does not win against outwards pressure, and it's just pushed off as a stellar wind.
What's pushing the red giant outward?
The red giant expands as you run out of the fuel inside. Yes, hydrogen. And then there's a second phase when you run out of helium as well.
Okay. Helium's the fuel then?
In the second phase. So you burn heavier and heavier elements until you run out of things you can fuse.
I see. Great.
Thank you for a wonderful talk. You presented two different hypotheses or models for planets to be in the right region around white dwarf. In the second one, with the second generation planets, what is the most direct observational evidence that we can think of to determine if something is a second generation planet? Is that been done?
Yeah, so we do have evidence, not around a white dwarf, but around a neutron star. So neutron stars are similarly the remnants of high mass stars. And the first planets ever discovered were found around a spinning neutron star. And it was kind of multiple planets in the same systems, pretty close to the star, but very small planets. And it is impossible that those were there when the neutron star was a main sequence star, because the phase of stellar evolution would have been even more violent and destroyed them. So people have essentially proven that these had to form via second generation formation. And the fact that you have multiple planets in the system is consistent with things forming from a disk of material at the same time. So that is evidence we have that second generation planet formation does occur. As for whether it can occur around white dwarfs, we don't have any exact systems that have to be formed via second generation planet formation yet. So we're still trying to find that evidence.
I had two sort of related questions. One of which was, as the giant star expands, obviously the point source approximation of gravity becomes less valid, and so I was wondering if tidal deceleration could provide a countervailing effect to the conservation of angular momentum that would expand the planetary orbits and cause them to migrate out. And then related to the migration, I was also wondering, would it be possible for inner planets to dehydrate but survive and then be rehydrated as type 1 planets by a nearby type 2 event or by disruption of the stellar Oort cloud, causing a new bombardment of cometary material?
Yep, so two great questions, and on both you have the exact right idea. So on the first one, yes, there will be tidal effects caused by the red giant that are more complex than the picture I showed for these outer planets, especially for things that are kind of closer to the red giant physically. Their orbits will be affected by tides from the red giant. Some planets that are not physically engulfed will actually potentially be disrupted and have their orbits changed enough that they'll spiral inwards and be destroyed anyway due to these tidal forces. There are other effects that these tidal forces can also have, which some students that I work with are working on seeing how it could affect giant planets that might survive the red giant phase but have their structure significantly altered. As for your second question of, could you take a planet that had its ocean completely lost and then resupply it from comets that supply additional volatiles, which is kind of the same idea as what we think happened here on Earth, potentially. Haven't fully proven it, but it's a good theory for the delivery of volatiles to Earth's surface. Totally feasible. In fact, the evidence that we have that cometary material accretes onto white dwarfs does mean that there is probably a flux of comets through the system. So we still haven't put the pieces together to determine if that flux of comets will happen in the same systems where you have these planets, but I think that's a good hypothesis, and it definitely could be a solution.
So one of the emailed questions is maybe related about the sources of water, but in this case, frozen water on the planet itself then being liquefied by tidal forces.
Yes, yeah, so that is a very good point, which is any of these planets that survived, if they had water on it, if they already had water on their surface, it would be in a frozen form on the main sequence, and some of it would probably remain in a frozen form until the tidal migration started. So all of this water that was retained probably did start frozen and then was melted via the heat produced by tides. So I think, yes, it did start frozen, and we just hope that there's enough heat to melt it into a liquid form by the time it gets to the habitable zone.
Hi, thank you for the talk, and this may be a basic question, but I was wondering, before the red giant phase, what ruled out the, because I presume in our solar system we're in a pre-red giant phase, so what ruled out liquid water, and then the possibility of habitability? Was it that they were too close, so it was too hot, or?
So the question is, what ruled out liquid water in what scenario?
In like the pre-stellar evolution, the pre-red giant phase.
Oh, so on the planets in the habitable zone around a sun-like star, you could have water on them. On the planets that were further out in the system, the water would probably be too cold. So you could have water. I mean, there's a huge inventory of water on icy moons in the outer solar system. So it's probably plausible to say that water exists in frozen form on bodies past the ice line relatively commonly. The trick is just if it is in a frozen form, like most of the moons, not all of them. So Europa is a good example of a moon that actually currently does have liquid water. But if it's in a frozen form, then you're probably not going to develop life there. Was that your question?
Yeah, could it go from the frozen form to just being stably in a liquid form?
Yes.
In that, like the pre-red giant phase as well? Are those like?
Okay, good question. Yeah, so there would be scenarios where this could happen. So Europa is a good example. So Europa is being tidally squished, as our demo showed, in the same way that Io is by its interaction with the other Galilean satellites in Jupiter. And it should be, if it was not being squished in this way, it should just have an ice shell, pure ice. But instead, it has a subsurface ocean and then a layer of ice. So, I mean, this is actually an example of something that is actually probably habitable conditions, but an astronomer would not see it as habitable. But it does, in that case, there is liquid water on the main sequence somewhere where we don't think it should be.
Why wouldn't they really consider that habitable? Is it too like niche of a case? Or?
Well, so it's a good question. So astronomers would not consider it habitable because we've kind of limited our definition of habitability because we're looking for the things that are the most likely to be habitable. Now, planetary scientists and solar system scientists definitely consider Europa as a good target in the search for life, which is why the Europa Clipper mission is going there to teach us more about it. So the main issue and the reason that astronomers don't try to do that is we don't have enough information about the nuances of the orbits of planets that could cause these kind of special effects. Like the only reason Europa is a good target in the search for life is because it's being tidally squished enough that it has liquid water. Like we astronomers would not know that unless we understood exoplanet systems as well as we do the solar system, which we unfortunately do not.
Great, thank you.
So 5 billion years from now, where's the water on the Earth going to go?
It unfortunately will probably first evaporate into our atmosphere and then be disassociated into hydrogen and oxygen. Then the hydrogen will be lost via photoevaporation and some of the oxygen will go with it. So it will just be kind of out in space.
Bummer.
Bummer indeed. Good morning. You pointed out that for first-generation planets, the significance of the migration time scale, which seems like a fairly complex problem in terms of the gases going out, the planets coming in. I'm wondering if we have any ideas or working on probabilities of the excellent sort that you showed for the graph with the inclusion of general relativity in the other case.
Yeah, so it is a very tricky problem. And there is a scientist in the UK, Dimitri Veras, who's been working on this problem for decades, like before we even started finding these planets. And he has done a huge number of computer simulations showing processes that can create scattering events at different ages. And sometimes he's shown that it might take a few billion years for a scattering event to occur. The probability part is really hard, because it's a very stochastic, chaotic process, and we do not fully know the initial conditions, because if I show you the plot of the planets that we have actually discovered so far, what you'll notice about them is we've done a very good job at discovering planets in the inner parts of planetary systems, but this is the inner parts of the parts that are going to be destroyed. So the planets that we really want to know about for this type of theory is like these planets here and these ones here. And we haven't found a huge number of those yet. So I think to get those probabilities, we'll need to understand the outer part of exoplanet systems better, which hopefully upcoming missions like the Roman Space Telescope, which will launch later this year, will help us start to understand at least a little bit.
Raveen.
So my question is, even if you had primitive life or proto-life on a planet that's that close to the white star, help us understand the kind of radiation that's coming off the star. I imagine it could be some pretty weird stuff and could disrupt life and, obviously prevent stable nucleic acids from forming and things like that.
Yeah, so that is actually a very important point. The radiation is actually only weird while the white dwarf is young. So while the white dwarf is young, it will have a lot of X-ray and extreme ultraviolet radiation, like a lot. But as it ages and it gets cooler, the radiation will get less energetic. And so after a couple billion years, you're not actually probably going to have too much high energy radiation. There is actually a conflicting problem, which is that some of the theories of biogenesis, the beginning of life, actually require high energy radiation to start some of the processes of the development of life. So this is probably another case where you'll have a Goldilocks zone of like, you can't have too much of this X-ray and extreme ultraviolet radiation, but you also don't want to have none. So there probably is some optimal formation time from that perspective, but that's something no one has worked out in detail yet.
Related to that question, I'm curious if the the planetary nebula offers dramatic cosmic ray shielding, because as I was thinking about a white dwarf being potentially more stable than an outflowing, actively fusing star, that of course projects the stellar magnetic field out into deep space and really provides a lot of protection against cosmic rays that is lost when a star transitions to being a white dwarf. So I was wondering if the planetary nebula offers perhaps some equivalent level of protection, and if so, how long that might last for.
Yeah, so that's a great point. Probably not for very long, and it will not be as good as the protection provided by a stellar magnetic field. This is also something that an additional problem is that, so Earth has an intrinsic magnetic field generated by convection in its core, and this is something that happens because of the radiogenic heating that we have in our interior, but as it ages, that heating level will go down and down and down again. And if the core does eventually solidify, you could imagine a planet without even its own magnetic field. So then there would be no protection. So this is definitely an additional issue. Unfortunately, I have no answer to give you because no one has worked it out yet.
Okay, well, if there are no more questions, thank you so much again. Let's thank Juliette for this wonderful talk.